Okay, can you hear? Send a message, right? Okay, write down the topic. Write down the topic. Refraction, refraction through lens. Refraction through lens. Okay. So far we have discussed refraction, then refraction through prisms. Then this is another optical element, that is lens. So in this part we are learning about refraction through lens. So first of all, you have to understand what a lens is clearly. Below that, below the topic, write lens. Below the topic, below the refraction through lenses, write down lens. Here there is a explanation of the lens, right? Write down optical element, optical element made of a transparent medium, made of a transparent medium with at least a one curved surface, with at least a one curved surface. Right? So the optical element must be made of a transparent medium. It cannot be opaque, right? It has to be I mean transparent medium. Transparent mediums are what? Glass, water, or air. Those are transparent mediums. So the lens must be made of a transparent medium, and there must be at least a one curved surface. One curved means this surface can be like plane, at least a one curved surface, right? Okay, that is what it means. So you know that there are two types of lenses. Under that, under what you written, you can write. So first type we call convex lens. In front of that, write concave lens. Convex lens, then concave lens. So when you are given a lens, you should be able to identify whether it is a convex lens or a concave lens. So how do we separate these two? When you get a convex lens, the middle of the lens is thicker than the edges, right? Below this, right, middle is thicker than edge, right? So when you are given a lens, if it is thicker in the middle than the edge, so those types of lenses are convex lenses. Then there are concave lenses. Below that you can write edge is thicker than middle. Edge is thicker than middle, right? Okay. Then there are types of convex lenses, then concave lenses. You can take notes with me. and if you have any problem, send a message, right? So for a convex lens, these are the examples. The most simple form of convex lens is what we call a biconvex, right? Biconvex. So the shape of that lens is like this, right? So in this part, in this under syllabus, we only have to deal with these types of lenses, right? But you have to be able to identify other lenses as well, right? So this is a biconvex lens. Bi means both sides. So you can identify that middle is thicker, right, than the edges. Middle is thicker. Then we have plano-convex. Plano-convex means one side is plane, is still middle is thicker. These two sides are thin, right? Edges are thin. Then we have a converging meniscus. Converging meniscus. Converging means convex type, but one side is like this. Both sides do not have the same curvature, right? So curvature here is higher, here it is lower, right? So this shape we call that a meniscus shape. Meniscus shape, right? The curvatures are different here. That's the all difference. So it is a converging meniscus. You can draw this with me. Here we are further learning only about this lens, right, under syllabus, right? Then there are three main types of concave lens. I think you have taken these three. Then for the concave also, there's biconcave. So under concave lens, we will be talking about only about this one, right? But you need to be able to identify other shapes as well. Okay, so this is biconcave. Then again, we have plano concave. So one side is plane, other side concave shape. Then we have diverging meniscus. Meaning, so the here also that is the rule. The edge should be thicker, middle is thinner, right? So that is the how you identify the concave type. So edge is thicker. One side is like this, then the another side like this. You can draw it like so. One side has a concave shape, other one it is a meniscus shape, right? So that what we call meniscus. Again, you need to draw that. So the middle is thin, edges are thicker. So it is categorized under concave lens. So first you have to identify that. Okay, right. Okay, once you taken this down, write down a subtopic here. Write down optical center. Optical center within brackets capital C. Optical center subtopic within brackets capital C. Right? Okay. So when you get a lens, so after this we are only talking about biconvex and concave lenses. Okay. Optical center. How do you identify an optical center? When a light ray goes through a lens, if there is no refraction, then that point in the lens we call that optical center, right? Okay. So let's say you have this convex lens, biconvex, right? Biconvex. Now clearly understand this. So this is a biconvex lens. So since it is biconvex, both sides have the same curvature, right? This middle point is what we call optical center. So if you have a ray which goes through this center, the ray does not deviate. It just goes through, right? So that is the property of the optical center. It is right in the middle of the lens, right? A light ray can go like this. Again, I need to draw another diagram here, right? So half here, another half here, okay? Right. Then I can extend this curvature like this to this side. I can extend the curvature. And if you consider this surface, that curvature has a center. That is what we call a C1, right? Then this surface, that is a first surface, right? For the first surface, actually this is C2, right? This is second surface. This is first surface. For the first surface, you have C2 here. Then you can extend the second curvature surface. Then you can get the curvature of that surface. We call that center of that curvature, we can call that C1, right? Center can be called C1. So you can see C2 is here, C1 is here, okay? Then let's draw this for a concave lens as well for the comparison. Okay. So you have this concave lens. Then extend this surface. This is the first surface, this is second surface. Extend this surface. Now you have to understand that C1 is here because it is the first surface. Then for the another second surface, it is C2, right? Again, for this case as well, the lens has an optical center. If you think about a ray going through that, it doesn't refract. It just goes through the optical center. So it will be important when you are drawing ray diagrams, right? Okay, you can draw these two. Identify that C1 is here, but here it is C2. Here it is C1, right? Below this you can write, below this, I mean, commonly, right? Commonly for both. What you're writing here is common for both, okay? So you don't have to separate it. Okay, so C1 is what? Center of first curved surface. C1 is center of first curved surface, right? So first curved surface means this. Here you have the center of that curvature. But C1 here for this one, concave lens, right? Then C2, center of second curved surface. Center of second curved surface, that is C2. Another thing is, when you don't have to mark it here, but I did understand that when you join C1 and C2, we call that principal axis. You have to identify these names, right? Principal axis. When you join C1 and C2, those are the centers of each curvature surfaces, curved surfaces. So when you draw a line, here as well you can draw the line. You don't have to draw the line, you can understand that, right? So that is called principal axis. Okay, right. Then another one you have to understand is what is this? C2, C1, C1, C2, C1, sorry, C1, C. Here as well, right? C1, C. So what is that? This length is what we call radius of the curvature. We can identify a radius of the curvature. So C1C, let's call it R1. We can name it as radius of first surface. Then you have C2C, let's say R2, that is the radius of second surface. Radius of second surface. You have to clearly identify these terms, right? Then there will be, it is a flow. You have to understand that flow. Right. The thing is, there are different types of lenses. So the lenses we are studying, this R1 and R2, they are equal because these you have equal radius, right? So you can write if R1 equals R2, so those are called biconvexo-concave, biconvexo-biconcave, right? So that those are the lenses that we will study, biconvex and concave lenses. The thing is, these curvatures are the same for biconvex concave lenses, right? Okay. Done taking notes? Thumbs up, right? Okay. Below this, right, rays that go through, capital C, that is the optical center, go through capital C, do not deviate. Do not deviate. Right? Do not deviate. Okay. So these are the main terms you learned so far. So when you take the lens, we have the optical center, capital C. Then we have C1, C2. C1, C2. So those are the centers of curved surfaces, right? Then when you join these 2 points, C1 and C2, you have the principal axis. So when you are drawing diagrams, we use principal axis. To find that, you need to draw a line through C1 and C2. Then you have to think about R1 and R2. Those are the radii of each surface, curved surface. Then, given that those radii are the same for those curvatures, these shapes will be also same, right? Because the curvatures are also same. Having the same radius of curvature means you have the same shape at both sides, right? So then we say that it is biconvex or concave lens. After this, we will be talking about only biconvex and biconcave lenses. But you need to be able to identify these terms, right? Okay. Then another important thing when it comes to lens, it is really important. It is the focus, right? Focus of a lens. Let's learn how to get the focus of a lens. Write down the topic focus within brackets capital F, not simple F, right? Within brackets capital F. right? Under that, right, any lens has a primary focus, within brackets f1, and a secondary focus within brackets f2. Okay. Right. So you can identify the primary focus and secondary focus. So how do you identify that? So when you get a light beam, parallel light beam that is parallel to the principal axis, it always converge into the primary focus, right? If you have a light beam that goes through the secondary focus, after refraction it gets parallel, right? So that is how you identify the secondary focus. I'll explain that. Under that, right, what you write down, focus of a convex lens. Focus of a convex lens. Right. So this is what it means, right? You can draw this with me. So if you have a rays that goes through secondary focus f2, the thing about secondary focus is, if a ray goes through secondary focus after refraction, that those light beam, so this is a light beam, right? Not only two rays, there are a bunch of rays like this, not bunch of, there are so many rays, but all rays goes through f2. If they go through f2, which is the secondary focus, always what happens is, after refraction those rays become parallel to each other, right? So that is how you identify secondary focus. Usually the secondary focus, not usually, it is always secondary focus is at this side. Given that light goes to this side, secondary focus is this side. Then how do you identify the primary focus? So opposite happens in the primary focus. When you get parallel light beam, it converges into the primary focus. For a convex lens, right? It converges. Okay, draw those two. Now I think you understand that, right? If the rays goes through f2, secondary focus, after refraction they become parallel. If a parallel beam incident, then after refraction it focuses onto the primary focus. Okay. So the primary focus is always other side of the light ray. Secondary focus is this side, given the light rays goes to this side, right? Okay. Another important thing you can understand is, actually the rays are goes through, actually the ray goes through both focuses, right? So we call these focuses of a convex lens as real focus, right? Because actually the rays go through these focuses. You can understand, right? So these are not dashed lines. Actually the rays goes there to the focus. So those are called real focuses. Under this, right, since rays actually go through focus of convex lens, focus of convex lens, those are called real focuses. Those are called real focuses. Okay, right. Then write subtopic focus of a concave lens. Focus of a concave lens. That is capital F, right? Focus means capital F. Focal length is what we call simple F. Focus is capital F, right? Okay. So how do we identify secondary focus? So what's the requirement? To identify the secondary focus, you have to send the rays. So after the refraction, those rays becomes parallel. That is the only that is the way to identify the secondary focus. Okay. So you know, for a concave lens, primary focus is this side, secondary focus is other side, given that light goes to this direction. Okay. So let's say secondary focus is here, f2. Then light ray supposed to go like this, but it is obstructed by the lens, right? Then another light ray, which also is targeting f2. But actually the ray cannot go like this, right? Because there's a lens. So what happens is, this ray gets, here it is converged, right? Converged means the ray was going to go like this, but it was converged. Here a concave lens diverges. Diverges means ray goes like this, but it bends away from the principal axis. It goes like this, right? So now you can identify the rays are going to go to the secondary focus, but after the refraction, so what's the property of the secondary focus? After refraction, those rays becomes parallel. Okay. Then we need to identify the primary focus of the concave lens. So what do we use to find the primary focus? We have to send a parallel beam of light. So let's see what happens when you send a parallel beam light. So after refraction, it has to bend away, right? Away from the principal axis. So the primary focus is here. So it is as if the light rays are coming out of F1 here as well, right? So to always, in both cases, to identify the primary focus, we have to send a parallel beam. To get the secondary focus, the rule is after refraction, the rays have to be parallel. Parallel primary focus. So after become parallel, it is a secondary focus. So you have to clearly understand those differences. Another thing is, you can see that the rays are not actually going through F2, right? We have drawn dashed lines, right? So the rays are not going through F2. So meaning of that is, for a concave lens, both focuses are not real. Not real means those are called virtual focuses, right? Both have virtual focuses. Done. If you're done drawing that, let me know. Right. Below this, write down rays actually do not go through rays actually do not go through focus of a concave lens. Focus of a concave lens. Therefore, those are called virtual focuses. Right? So you have to understand as I'm explaining, okay? So those are called virtual focuses. We don't usually don't say like not unreal focuses. Okay? So the name is virtual, right? Virtual focus. Then below this, put an asterisk mark and write main focus of a lens is f1. F1 means primary focus, main focus. Then according to the diagram, C is optical center, CF, from C to F, right? C to focus is what we call focal length. CF equals focal length, simple F. You can name it focal length. Write it down. CF equals simple F, which we call focal length. Right? Then another asterisk mark. Write down. If both sides of a lens have the same medium, if both sides of the lens have the same medium, below that write CF2 equals CF1. Do you understand that? So you have a F2 here, right? F1 here, C here. Both sides, usually the glass is, in most cases, lens is made of glass and both sides have air, right? Usually, in most cases, CF2 and CF1 are equal. CF2 and CF1 are equal, right? Because both sides we have air. But there might be a case like, let's say this side has water, this side has air, right? Then you won't have the same length. Then you cannot say the CF2 equals CF1, right? In that case, you cannot say that. But here it is CF2 equals CF1. In most cases, we get this, right? Like 99%. Right. Below this, right, another asterisk mark. Simple F, that is focal length, right? Simple F depends on following factors. Simple F depends on following factors. So what are the factors? Write down first one. Radii of curvature, curvature of lens surfaces. Radii of curvature of lens surfaces. Right? Within brackets R1, R2. Remember R1, R2? So these R1 and R2 determine the shape of the lens. It determines the shape of the lens, right? R1 and R2. By changing the curvature, R1, R2 changes, right? So you can understand that focal length depends on R1 and R2. There's an equation for simple F and the combination between R and R2, but it is not in the syllabus, right? You just have to know this stuff. Right, second one, write down material, second one, material, lens is made of, material the lens is made of. Material lens is made of, whether the lens is a glass, air, like water, so those can take those shape of a lens, right? So depending on the focal length depends on that material as well, right? Third one, medium. Medium lens is placed. Medium lens is placed. Medium lens is placed, right? So if you have the same lens, let's say here the medium is air, outside it is air, here the medium is like water. If the focal length for air is somewhere here, when it is water, focal length will be somewhere here, right? Okay. Even if it is the same lens, but if they are in different mediums, then we have different focal lengths, right? We'll clarify that using an example, right? Below that, write example. Write down, if same glass lens, write down, if same glass lens if it is, sorry, not if, the glass, sorry, the same glass lens, not if, right? From the beginning, the same glass lens, the same glass lens, if it is placed in water, if it is placed in water, if it is placed in water, instead of air, if it is placed in water instead of air, its focal length is higher. Its focal length is higher. Comma, since the difference between simple n, difference between simple n means what? Refracting index, right? Difference between simple n is less due to less deviation, is less due to less deviation of rays, due to less deviation of rays. Right. Now I'll draw a diagram so you will understand what I'm saying, right? So we are taking the same lens, right? Lens, now it is in air. This lens is in air. Then again the same lens, but this time we put it in water. This is made of glass, right? Glass lens. Here medium is air, here medium is water. Right. So for air and glass, what are the refracting indexes? For air, refracting index is 1. Okay. For glass, how much? 3/2, right? That is 1.5. Okay, here it is water, then glass. For water, refractive index is 1.3 something. For glass, it is 1.5. Okay. Here, what you have to understand is you need to get the difference between refractive indexes. So here, what's the difference? 0.5. Here, the difference is 0.2, right? 0.2. So if the difference is higher, what happens? So if you think about a parallel beam, so using a parallel beam, we can identify the focus. Here, difference is higher, right, than here. So what does it mean? If the refractive index difference is higher, there's going to be more refraction. So compared to glass, air is a very rare material. I mean, very rare medium, right? So in that case, the rays bends too much. Understand? Because the difference between those mediums is large, right? Deviates way more in this case, like this. It bends like this, right? So here the focal length is this much. But what happens here? Difference is not that much, right? This is glass and water. So it doesn't deviate this much. It will deviate somewhat like this much. In that case, even if it is the same lens, since the mediums are different, here the focal length is higher. Okay? Okay, take it down. Get these two as well in front of them, right? So looking at this, the sentence you have, you must understand that. If you don't, let me know. Thumbs up if you have taken it. Thumbs up if you're done, right? Right. So I think this is clear, okay? This is clear. The sentence, this diagram is to explain the sentence. Right. Below this, right, put a asterisk mark, then write in a rare medium, comma, first point, convex lens show converging properties. Convex lens show converging properties. Convex lens show converging properties. Converging means converge, right, to a point, or bends towards the principal axis. That is converging, right? It always doesn't have to be a point. If the rays bends towards the principal axis, then we say converging, right? Okay. In a rare medium, first point, convex lens shows converging properties. To the same line, right? Therefore, convex lens is called converging lens. Convex lens is called converging lens. Okay. Similarly, for the another point, write down concave lens show diverging properties. Concave lens show diverging properties. So it is called a diverging lens. So it is called a diverging lens. Okay, so that it is another name for convex and concave lenses. For a convex lens, it is a converging lens. Cave lens, it is diverging. Right? Diverging means away from the principal axis. Converging means towards the principal axis. Remember like that, right? Converging means towards the principal axis. In some cases, it doesn't converge to a point, but always those rays, if it is converging, they bends towards the principal axis, right? Okay. Then you need to have, then we need to draw ray diagrams, right? Ray diagrams. You need to have an understanding how the images are formed, the nature of the images. Without drawing ray diagrams, you have to understand how the properties, the positions, roughly how those images are made. So when it comes to MCQs, you cannot use equations. Therefore, you need to have a rough understanding where the positions of images going to be, right? So when we think about ray diagrams, there are three types. There are three types of images. When we think about convex lens, right? Convex lens forms real images. Remember, convex lens. If you have an object here, convex lens made real images at this side. Another different type is convex lens also can create virtual images at the other side. That is the second type. Then the third type is concave lens. Concave lens always makes virtual images, small virtual images. So those are the three main types of image formation, right? Okay, write down. Like a subtopic, right? Three main cases of forming image. Three main cases of forming images. Three main cases forming images. Okay, I'll name them A, B, C, right? Okay, simple A, right? Simple A. Write down. Forming real images by a convex lens. Forming real images by a convex lens. Right. So, when forming real images by a convex lens, you need to place the object beyond F, right? F means beyond the secondary focus. Under that, right? So this happens. This means forming real images by a convex lens, right? Under that, right, when object is placed beyond f, right, beyond f, so it is like this. So if you have the lens, so here we are not always saying which focus, right? You need to understand that. So this is actually the secondary focus, okay, given that light rays comes to this direction. So usually we place the object here. So beyond f, then we have 2f here at the same distance f, then again 2f. So beyond f means somewhere here, right? Somewhere in this area. Let's say you place the object here. So there are at least we need to have 2 rays to find the position of this image. So you can draw a one ray which goes through the optical center. It does not deviate. So we know where that rays goes after refraction. It just goes straight without any deviation. Then you can draw another ray that is parallel to the principal axis. So that ray, we know that. Use a ruler when you are drawing these, right? That ray always goes through the focus. Right? Here the object, you have the inverted image here. And you can see for any position beyond f, it is always going to be a real image. So it is a real image. Actually the rays goes to that, right? That is what we call real. So you can take this image on a screen. If you place a screen here, you will see the image of that object here, right? If it is virtual, you cannot do that. Using a ruler, draw this. So what are the properties? If you're done drawing this, let me know. Right. So once you know the position, you should be able to say the properties of this, right? Write down. Below this, right? Image is, first point. Behind means this side, right? Front means this side. Image is formed, first point, formed behind and beyond f. So it is beyond f, right? Beyond f. When they say f, saying about this f, right? Behind and beyond f. So if it is this side, we know the rays actually goes to that point. So the another point you can say real. If it is this side, once you know the position, you should be able to say all those things. Another thing is inverted. You can see it is inverted. Those stuff you know. Then lateral inversion. Right? So the lateral inversion, you need to clarify that. So when you think about the plane, this board, you can see the image is inverted, right? The same thing happens sideways as well. So it is like this, right? So let's say this is the object. Then to identify that, we have we darken a one square. So according to this, the image of this, it is magnified, the image. So when it is lateral inversion, this side goes to this side, but you cannot identify that, right? This darkened side also goes to the other side. Then the white side goes to this side. Even these two changes, it doesn't make a difference. But this side, you can clearly identify that. So this is what we call lateral inversion. This flipping in a horizontal plane, it flips or it inverts in a vertical plane. You can see that here. The same thing happens in a horizontal plane, right? So that is called lateral inversion. It is enough at this level what lateral inversion means. So when a convex lens makes real images, that image is submitted to the lateral inversion as well, right? Lateral means to this side in a horizontal plane. In both planes, there's the inversion. This is only to explain the lateral inversion, right? To get the real image, this actually goes to the here, because there's a vertical inversion as well. This is just to explain the lateral inversion. Below that, right, lateral inversion. It laterally inverts and also vertically inverts, right? This is only to explain lateral inversion. Okay, so that is the first type, simple A. Then write, did you draw this? Okay, so that is simple A, right? Now simple B type. Write down in front of simple B. Forming virtual images by a convex lens. Forming virtual images by a convex lens. Right. So this is the another type, virtual images. Right. So this happens below that, right, when the object is within focal length. Right. We have this lens here, f, here 2f, here f, 2f. Then you place the object within focal length, means this is focal length, so it is within, right? Right. Then we draw two rays. One ray going through the optical center, another ray parallel to the principal axis, which goes through capital F. And you can see at this side, it is not converging to a point, right? It is going like this. So it won't create an image at this side. Then you have to extend these two rays to the other side. So now you have the converging point. The thing is, you can see this is a virtual image. The rays actually doesn't go to this direction, right? Rays goes to this direction. But to get the position of the image, you need to extend this to the opposite side. So this image is called a virtual image, right? And it is not, it is magnified, but it is not inverted. It is not inverted, right? Okay, take this down. Use a ruler when you are drawing ray diagrams. You have to draw so many ray diagrams and practice these, right? Thumbs up if you're done. Right. Here as well. So what are the properties? Write down image is, comma, first point. First you need to mention the position. What's the position? Beyond O, right? Not F. Sometimes the image can be made here as well, right? A virtual image can be made here as well. So we say the image is formed beyond object. It is always beyond object, right? And this side we call in front of the lens. This is what we call in front, right? In front of lens. This is behind. This side is behind. This is in front. So you need to understand those words when you're doing questions. Okay. The image is, write down, formed. First point, formed beyond O, beyond O means object, beyond O and in front of the lens. Beyond O and in front of the lens. Right. Another point, write down virtual. Write down within brackets, cannot be on a screen. Virtual means within brackets, cannot be on a screen. Then third point, upright. Third point, upright. Upright means not inverted, right? You can see it is not inverted. It is upright. Another thing is no lateral inversion. So laterally as well, it is upright. But we don't call upright. We call that no lateral inversion. It doesn't flip, right, the image. So it is no lateral inversion. Right? Okay. Then there's third type of ray diagrams. Write down simple C. So that type is concave, right? Concave type. Write down simple C. Form in virtual images. Form in virtual images using a concave lens. above both types are convex, right? Now it is concave. You have to understand as I'm explaining this, right? I know, not explaining, as you are taking the notes. Forming virtual images using a concave. Okay, so this happens below that, right? Put a dash, then write when object is placed anywhere, when object is placed in front of concave lens. Right. Now you have the concave lens. Let's say F here. You can place object anywhere, even here as well, right? Within focal length as well, you can place it. Doesn't matter. Ray which goes to the optical center doesn't deviate. Ray parallel to the principal axis. It does not bend towards the principal axis, right? It bends away. Since it is parallel, it bends away so that you can extend this ray so it goes through F, right? So when you take this ray and this ray, they meet here. So the position of image should be here. So the image is made here. You can see it is a virtual image, right? Because only one ray goes there. Another ray is actually a virtual ray, right? So it forms a virtual image. Okay. So when it comes to concave lenses, when you place the object anywhere in front of the lens, always it creates a virtual image, smaller virtual image between F and the optical center. Take down the ray diagram. Right. Below this, right, image is comma, first point, forms between images, first point, formed between where F and C. F and C. Another point, virtual. Another point, it is virtual, right? Cannot take it on a screen. It is a virtual image. Third point, you can see it is upright. It is not inverted. Third point is upright. Since it is upright, for a laterally also there is no inversion, right? No lateral inversion. No lateral inversion. So you can understand for lenses, if it is not inverted, always it is going to be, there's no lateral inversion as well, right? But for a mirror, it is a different case, right? So when you look from a mirror, you don't see an inverted image, right? You see upright image, but laterally the image is flipped, right? Laterally. But you cannot see that because you are we are symmetrical, right? So we don't see that. But if you place some letters in front of a mirror, you can see the lateral inversion. but there's no vertical inversion, right? In a vertical plane, there's no inversion. There's a lateral inversion in a mirror. But for lenses, it only happens if there's the inversion. If the image is inverted, there's a lateral inversion as well for lenses. So I have to remember those, right? Right. So it is no lateral inversion. Okay. Right. Then write a subtopic. Write a subtopic. Draw in ray diagrams. Draw in ray diagrams. Okay. So whenever we draw ray diagrams, there are 6 types of rays that we have to use. We'll see that, right? You can draw this with me. When you take there are 3 here, right? Okay, right, draw like that, right? A convex lens and a ray which goes through the optical center. It doesn't deviate. So we already used that. Another type of ray, if the ray goes through secondary focus, what happens? After refraction, it becomes parallel. Then the third type, parallel to the principal axis, after refraction goes through the primary focus. So when you are given a ray to detect the path of that ray, you will have to use one of these if it is a convex lens. So then we can discuss the same case for a concave lens. Goes through the center, doesn't deviate. Here, goes through the secondary focus. Actually, the secondary focus is here for a concave lens. It actually cannot go to that, right? Because there's a lens, right? But it is aiming to the secondary focus. So if it is secondary focus after refraction, it is going to be parallel to the principal axis. Then the another type, parallel ray to a convex lens. If you get a parallel ray that parallel to the principal axis, right? To the principal axis after refraction, it doesn't deviate like this, right? It deviates away. So when you extend it backwards, you will meet the primary focus of the concave lens. Okay, take that down, take those down and let me know. So whenever you have to predict the path of a ray after refraction, you will have to use one or two of these. Actually, two of these, right? Done. If you have any problem, let me know. Thumbs up if you're done. Right. Then there's something called focal plane, right? Now we talked about focus. Then there's another thing about focal plane, right? Up to here, we discussed parallel rays. So this is a parallel ray, but that parallel beam of light, but it is parallel to the principal axis. But in all cases, the beams will not be parallel to the principal axis, right? So for the concept of focal plane is useful when you get a beam that is parallel but not parallel to the principal axis. This is what it means, right? So if you have a beam like this, it is parallel to the principal axis. So we know that it converges to the focus. Or if it is a concave lens, it is as it diverges from a focus. But the beam could be like this as well. It is still a parallel beam, but not parallel to the principal axis. So in that case, we'll need the concept of focal plane, right? Write down the subtopic focal plane. Right. Under that, right? Plane that goes through the focus normal to principal axis plane, right? Plane that goes through the focus normal to the principal axis. Okay. Right. Write down first point, then I'll explain that. First point, put a point, write down a parallel beam that is not parallel to the principal axis. Understand? Parallel beam, but it is not parallel to the principal axis. Converges to a point on focal plane. Okay. Then next point, write down a parallel beam that is not parallel to principal axis diverges from a point on focal plane Okay. Took it down. Done, right? Thumbs up if you're done, right? Okay, so this is what it is, right? So the first point, to explain the first point, I'll draw this diagram. I'm going to draw another diagram here for the concave. Okay. So what has happened here? You have a parallel beam, but the thing is, it is not parallel to the principal axis. If it is parallel, it just converges to the focus. But here, let's say focus is here. It is not it is not parallel to the principal axis. Then what happens? In that case, we need a focal plane. This is a plane, right? Not a line. Actually, it is a plane like this that is normal to the principal axis and goes through focus. Like this, right? I'll draw it like this. This is what we call focal plane. So according to the sentence, it doesn't converge to the focus, but to a point on the focal plane. So how do we figure out the point? There's a one ray which we know. You know that this is not two rays, right? All the rays are parallel to the other rays. You can draw any number of rays here. It doesn't matter between these two. This ray, the path of this ray after refraction, we know that. It just goes straight. Now it is incident on this point. Again, we know all the rays converge to a one point. Now we found a point for a one ray. Then what should happen to the other rays? Those rays as well must converge to that point, right? Understand? It doesn't stop here, right? Just rays goes, but it converges to this point. So to find that converging point, you always have to draw this another ray which goes through the optical center. So that is what you do. Take it down. I need to draw a similar diagram here. Take it down and thumbs up. If you don't understand, let me know. Right. Then we'll think for the second case. Second case means for the concave lens. Okay, concave principal axis. Again, you have a beam that is not parallel to the principal axis but to each other. So what do? We need this ray. We know the path of that ray. But the thing is, here you have the secondary focus, right? Here you have the primary focus for a concave lens. Then we draw, here also we draw that for the primary focus, right? Here also we draw it for the primary focus. Okay, now you have this focal plane. So which ray do we consider? After refraction, it has gone like this. You know that to this side, we don't meet a focal plane, right? Focal plane of the primary focus. We don't meet that. So what do? We need to extend this backwards to find that position. It can be dashed lines, but you don't see that, right? Because already there's a ray here. So this ray you can extend backwards to this side or this side. Then you can find the converging point. Actually, this is a diverging point, right? Not converging point. This is converging point. This is actually diverging point. The rays diverge from that point. Okay, now what happens? Okay, all the rays has to diverge from this point. So this ray also diverge from this point. If it diverge, actually the rays don't go there, but you can draw dashed lines. Diverge means like this. Okay, after refraction, you know the path of this ray now. What about this one? This ray also as if it is diverging from this point. When you extend that, it diverges like this. This side, this side, this side. Right? Okay, take it down. You can draw this again, right, later. And you have to understand this somehow. We did the same thing, right, as is here. This is easy to understand. If it is complicated, this will be a little bit complicated. But it is the same theory, right? Thumbs up if you're done. Right. Below this, right, below this diagrams, right, this can be used, this can be used to draw the path of, to draw the path of a ray, path of a ray after refraction, to draw the path of a ray after refraction. Okay. So I draw these diagrams from this side and this side, so you can compare those two later, right? Okay. So example, for this one also this side and this side, right? Two example, one example convex, another one concave, right? So let's say, so in like a MCQ, they have given this ray. There are many MCQs like this, right? You are given this ray, and they ask the path of this ray after refraction. How do we find that? Focus is given, right? Here you have the primary focus, the secondary focus. We need primary focus. So what do? We draw the focal plane through the primary focus. Here also you can draw it, but primary focus is what matters. Drew the focal plane, right? Then what do we know? Do. For sure, we know this. You can have a ray. There may not be actually a ray like this, but the thing is, you are only given one ray, right? Only this ray. But parallel to that ray, we do another ray which goes through the optical center. Why do we do that? Because we know the direction it goes after refraction. And the point is this, right? We only have this one, first case, right? Then this second ray. If you want, you can draw this in dashed lines. It is something we created in order to find this position. This can be dashed lines. Okay, first one, second one, right? First we had this ray, then you have this one. Then we know this point, converging point. Then what does it say? This ray has to converge to the point. Okay. Now we know the direction that this ray goes after refraction. So I have to do that, right? Understood? This is really important, right? Okay. This example. Then let's get an example for this order is named, right? That is why we put 1, 2, and 3. First one, we are already given the ray, then the created ray, then you can know the path of the refracted ray. Press draw this one. If you are done, thumbs up. Right. Let's think this for a concave lens now. Okay, for a concave lens, we are given this one. First, that this is all they have given, right? Then they asked, and focus as well, right? They have given focus as well. Here focus. Here you have the primary focus. You need primary focus. So what they ask is, what's the direction of this ray after refraction? What do we do? Through the primary focus, we have this focal plane, primary focus, right? Then we draw the parallel line, parallel ray to this ray. It is a creation, right? That's the second step. Okay, now we know the point which intersects the focal plane. Okay, so from this point, now this is the point, right? So for a concave lens, so that is a diverging point. The rays diverge as if the rays diverge from that point. Here it is converge to the point. Here it is diverge. Okay, if it diverge, should be the direction of this ray? It has to diverge like this. It comes here, then goes there. Take it down. Now we know that. So third step. Thumbs up if you're done. Right. You have to understand these, right? 100%. Right. Then a separate point, put an asterisk mark here, and write down. In a dense medium, comma, so what happens to the convex lens? Convex lens shows diverging properties. Got it? Convex shows converging properties in a rare medium, but for a denser medium, if the medium is denser, right? For an example, let's say you have a glass cube, and inside it there's a hole shaped like a lens. So this is rare. Lens is rare, this is dense. So in a case like that, this lens behaves as a diverging lens. Even if it is convex lens, it behaves as a diverging lens. Okay. Write down convex arrow diverging properties. Then what happens to concave? concave lens, now it becomes a converging properties. Okay, converging properties. So this is what happens. Below that you can draw this. You have a converging lens. I mean convex lens, but it shows diverging properties because the medium is denser. Understood? Diverging. Then this behaves as a convex lens because the medium is dense. Draw those two. Okay. Done, right? Thumbs up if you're done. Right. Then write the subtopic lens equation. Lens equation and sign convention. Lens equation and sign convention. Right? So you know that we can actually derive lens equation. For each cases you will have different types of equations in terms of V, U and F. For an example, for a convex lens, when it creates real images, you will have a similar type of equations, but those signs could change. To solve this, so there are three types, right? So for each type there will be a different equation, right? The use of the sign convention is once you apply the sign convention, you will always will have the same equation and you can easily solve questions, right? Once you apply the sign convention, we don't have to derive those stuff. You just have to know that, right? So the lens equation, this is also called common lens equation as well. 1 over V minus, just write it down, 1 over F. So V is image distance, U is object distance, F is focal length. Okay. Below this, right? Once when the sign convention is used, for any scenario, this equation can be used. So you have to apply the sign convention correctly, right? So these are the rules that you have to follow when you are thinking of this equation. First, write down first one. All the distances are measured, all the distances are measured alone, principal axis from C, from optical center, right? From C. Second rule, to the direction of light, minus, right? Then below that, right, to opposite direction of light, write here positive. Okay. So this is what it means. Again, we can compare this to a convex lens and a concave lens. Let's say convex. Let's say the direction of light to this side. It could be this side as well, right? Now the direction of light is to this side. So according to sign convention, everything is measured from the optical center. From here to here or here to here. Any measurement to this side, we take it as a negative. Any measurement to opposite direction of the light, we take it as positive. Okay. And we know primary focus is here, right? If the light coming from here, primary focus is here for the convex lens. You can take down this with me. Then concave. You know the primary focus here. Same case, right? If the light, this light coming from this side, any measurement to this side negative, opposite side positive. That is what it means. This side negative, this side positive. Opposite side of the light for both cases. Okay, take it down. Right. Then below this, right, according to sign convention, comma, according to sign convention, comma, first point, for convex, so you can see convex lens, focal length is negative, right? We consider the primary focus. So it is to this side. So F is negative. Okay, take it down. Then for concave, F is positive, right? To this direction, F is positive. Focal length. Then another thing, if you have a real image, Real image means image is formed at this side, right? If the image is formed at this side, usually it is a virtual image. So this side, you have to measure to this side, so it is negative. For real image distance is negative because we measure to this side from the optical center, negative. Then for virtual image, if the image is made at this side, you have to measure it to this side, right? So it is a positive, U positive. uh, Here within brackets write down sorry, virtual image, right? Image distance, it is V, right? Not U. Still we are talking about image. Then real object, no, just write mostly U is positive. Below that point, right? Mostly U is positive. Why is that? We normally place the object here, right? There's something called virtual objects. You will learn that later. Usually we place the object here, right? So you can see you have to measure it to this side. So U is usually positive. Some cases it becomes negative for like virtual objects. We'll talk that separately. But in most cases it is positive, U. The reason the object is placed, within brackets, right? The object is placed in front of the lens, usually, or mostly. Mostly the object is placed in front of the lens. Okay, done. Thumbs up, right? If okay. Let's do a question. Write down Q, capital Q. Here write down a thin object is placed at a 12 centimeter distance in front of a convex lens with focal length 10 centimeters. Full stop. Find the position of the image. Okay, now listen, this is the method, right? You have to correctly apply sign convention. You just write the equation first. That is just what you do first, right? Then what do you do? So the focal length is given and they say it is a convex lens. So you know focal length should be minus, right? Because it is a convex lens. Focal length minus 10 in front of the lens. Object is placed in front. So you know that u should be plus 12 centimeters, right? Then you what you need to find is v, right? Then you just substitute it here. U is 12 plus 12, right? Doesn't make a difference, but plus 12. You have to correctly apply that, otherwise you will get a completely different answer. Equals f is minus 10. Okay. Now we done applying the sign convention and the substitution. After that, you just do a usual simplification, right? So it is a minus here, minus 1 over 12 goes to the other side, 1 over 12. This minus plus minus, minus 1 over 10. I think 60, common denominator. 5, this is 6. Okay, we have minus 1 divided by 60, 1 over v. You need to find v, right? So v is minus 60 centimeters. We are given the answer in sign convention. Minus 60 means what? The image has to form, if the object is placed here, image has to form at this side, like this. Got it? Okay, take it down. Thumbs up if you're done. Right. Then we have to talk about linear magnification, right? Linear magnification. Write down the topic, linear magnification. Within brackets, simple m. Linear magnification, simple m. Write down the definition of linear magnification. Write down ratio between image height, ratio between image height within brackets capital H and object height within brackets simple h. To the same line, right? This also is equal to ratio between, this also is equal to ratio between u and v. Okay. So according to the definition, linear magnification is what? Image height divided by object height. And this also is equal to, image means image distance divided by object distance. When you use this, you need to only take the positive of this, because v and u can be negative as well, right? So you put modulus signs like this, right? Because for the magnification, we don't need a negative or a positive something, right? We only need how many times the image gets bigger than the object, right? How many times the image as the object, right? Okay, take it down, and below you can say if h is larger than simple h. H means image height. Image is larger than the object. When you divide it, what happens? Linear magnification is greater than 1, right? It is greater than 1. If you don't understand, tell me. It is greater than 1. Then if h is smaller, or let's say equal to image height and object height equal, then what happens? These are equal, right? Then linear magnification is 1. There's no magnification. Object and the image, they are the same height. Third case, if capital H is less than simple h, image is smaller now, then what should happen? Linear magnification should be less than 1. Okay, take it down. Below write example m equals 2 means height of the image height of the image is twice the height of the object. Height of the image is twice the height of the object. Right? Understand, right? It is twice. So when you simplify this, you get 2 there. This is 2h, this is h. To the same line, right? And also image distance is twice the object distance. Image distance is twice the object distance. Okay, right. Then write down the topic. Variation of V, simple V and simple U. Variation of simple V and simple U. For a convex lens, you need to remember these graphs. So let's say you have V for the y-axis, U for the x-axis. U is always positive, right? So we only need positive side of the graph for U. But negative side of V can be negative as well. There are virtual objects that in those cases U becomes negative, right? But here you don't have to. So you know these distances. Simple F here, right? It is a positive value, right? Understand? simple f, positive value, then let's say 2f, this point and beyond. So you are placing the object somewhere here in this region, right? Then we are check what happens to the image, right? So you know that when you place the object between lens and the focus, it always creates virtual objects behind here, right? So the virtual images. Virtual images means image distance is positive. So this is the region, right? This for this region, always it is virtual images. So the v value should be positive, right? Between 0 and f. Meaning when you place the object between lens and f, image always is formed in front of the lens. So it is a positive value. So the graph would be like this, only in the positive range, right? So you are moving the object from 0 to f, from here to here. You are bringing the object from here to here, moving the object. Then what happens to the object? Image. When you are moving the object from here, from lens to f, image moves from where? Image moves from 0 to infinity, right? When you are this is what happens. Let's say this is the image, this is the object. So you can move the object from here to here. Then what happens to the image? When you are moving it, image also moves. And when the object is at f, image is at infinity, right? Okay. Then we'll see after f. After f, what happens? So right after f, it is at the negative infinity actually. So for after f, all the images are real images, right? Remember, real images. So v values will be negative. They will be negative. They will be negative, but the images won't be created here. Images are formed beyond f, beyond secondary primary focus, right? So the graph will be like this. Okay, graph will be like this. If you want, you can have that 2f thing. So for 2f, other coordinate also is 2f. Okay, take it down. So this part is virtual. This is for real images. This is virtual images. Take it down. This length part is somewhat lengthy, right? But to understand optical instruments and human eye, you need to have a clear understanding of lenses, right? Right. Then write the subtopic. Special facts about special facts about real images. Real images formed by a real image just formed by a convex lens. Real images formed by a convex lens. Below that, right, if the distance between I and O, I means image, then O object, I and O is capital D, the requirement is D is equal or greater than 4F. Otherwise, you cannot form real images, right? Write this down. D greater than equal 4F. So here I'm only talking about a convex lens. So you have the object here, U, then the image here. Distance between object and the image. That is what we call the capital D, right? The requirement is capital D has to be greater than or equal to 4F. We can derive this, but it is not in the syllabus, right? It is a simple derivation, but it is not included in the syllabus. You just have to know this. In order to form real images, this is requirement. The distance between object and image, real image, right, should be greater than or equal to 4F. Okay, take it down. Right. So what you do is you will have a screen like this, and you have the object. Object. Let's say the lens is here, right? Then object distance, that let's say U, and this is image distance V. So as you are moving the lens to this side, this is screen, right? There's another position of the lens. So here image is created on the screen, but for this position also an image will be created on the screen. The thing is now the image distance, this is again reversibility of light. Now the image distance is equal to object distance. Object distance is equal to the image distance, right? So it will make a second case. This is the first case, second case. These are not two lenses, right? One lens at two positions. Draw that. This is the first case, then second case. Same lens at two different places, okay? Thumbs up if you're done. Right. Then write the subtopic. Images formed by concave lens. We already drew the ray diagram for this, but I'll draw it again. If you have the concave lens object here, let's say focus. So a small image is created like this. Okay. So here what you need to understand is what will happen if you move the object closer to the lens. Let's say to somewhere here. This ray does not change, right? But what about this ray? It goes like that, right? Can you see that the image is larger now compared to this image? This image is larger. Red image is larger. So the meaning of that is when you move the object towards the lens, the image gets larger, right? Image gets larger. Or another points we can say, if u decreases, v also decreases. Both are positive values. So from that we can draw a graph. Just draw this, but use two different colors, right? Object here, object here. Take it down. Done. Thumbs up if you're done. So I drew this to understand the variation between v and u, right? So according to this, v is positive always. Image is only formed within the focal length. So the maximum v can increase is f, right? Focal length. Okay. So you keep increasing. When you increase u, image moves to this side. But the maximum the image can be moved is to capital F. When the image moves to capital F, in order to move that to capital F, you have to move the object to the infinity. Right? So when the object distance is infinity, v becomes f. The variation is like this for a convex lens. So you can see V is only positive, right? So these images are virtual. It is obvious. For a concave lens, it is always virtual. Take it down. Thumbs up if you're done, right? Okay. Then we have to talk about virtual objects, power of a lens, lens compounds, combined lenses, those stuff. We'll do that in the next day, right? Because this is somewhat lengthier. So we'll do those parts at the next day. Are you free on tomorrow evening, 8 p.m. or something? Thursday, right? Tomorrow? Yeah. No? Mm. Okay, we'll do then on Friday 8 p.m. At the usual time, right? Okay, right. So we'll wind up here for this part. Otherwise, this will take like another 2.5 hours. We'll do that in the Friday next class, right? In the meantime, do the MCQs from the lens, from the pacer. Okay, right. Good night.